In this video, we are going to discuss the properties of salts and ions as weak bases, the relationship between Ka and Kb, and the percent ionization in reactions of acids and bases. When some salts are dissolved in water, they can either form an acidic or a basic solution. If the cation is a conjugate acid of a weak base, the solution is acidic. If the anion is a conjugate base of a weak acid, the solution will be basic. Some transition metal salts dissolved in water result in acidic solutions. Cobalt 2 chloride, zinc nitrate, and aluminum nitrate are acidic. Aluminum 3 plus is a cation, and it is a Lewis acid. A strong acid will have a weak conjugate base. A weak acid will have a strong conjugate base. As acid strength decreases, conjugate base strength increases. The weaker the acid, the stronger its conjugate base. If the acid is relatively strong, then its conjugate base is not holding to the proton, so it must be a very weak base. Relative strength can be estimated from the magnitude of the equilibrium constants, Kas. Conjugate bases of strong acids are weak bases. Examples here: perchlorate, iodide, bromide, chloride, and nitrate. They are weak conjugate bases of strong acids. The product of the ionization constants of an acid and its conjugate base is equal to the ion product of water, or Ka times Kb is equal to Kw. Many reference books give tables for only Ka values because Kb values can be calculated using the relationship between Kw, Ka, and Kb. We observe that the products are made at expense of the reactants. On the first reaction is the dissociation of a weak acid in water and its equilibrium expression. The second reaction is a conjugate base of the acid in water and ion dissolving water. When the two reactions are added, the two ionization constants are multiplied. If we observe carefully, by eliminating common terms, we arrive to the ion product of water, that is Kw. Conjugate bases of strong acids are very weak. Every anion can be thought of as the conjugate base of an acid. For example, Cl- is the conjugate base of hydrochloric acid. Cl- is a weak base. The pH is neutral. When you have table salt in water, the Cl- is there and the pH is neutral. It's not sour. Now, if the anion is the conjugate base of a weak acid, the anion is basic. Fluoride anion is the conjugate base of a weak acid. When sodium fluoride is dissolved in water, fluoride takes a proton from water and makes the strong base hydroxide. The combination of chemical equations is to produce an overall reaction. It is the same operation as it is performed in the thermodynamics chapter in General Chemistry 1, applying Hell's laws. The operation with the equilibrium constants is similar to the ideas presented before. When we reverse the equilibrium reaction, we have the inverse of the equilibrium constant. What is new here is that we combine the chemical equations. The equilibrium constants are multiplied together instead of adding together as we did in Hell's law calculations. Thus, it is important that you take notice of this. When dissolving sodium fluoride in water, it yields the weak acid and the pH is basic. To work the overall reaction in blue, we first look at the equilibrium expressions. In the first reaction, we use the reciprocal of Ka because it is the reverse of dissolving the salt in water. The second chemical equation is the autoionization of water, which is needed because it is the only source of hydroxide which is part of the product of the beginning reaction. What is done here for fluoride applies in similar fashion for all anions that are the conjugate base of a weak acid. After combining equilibrium constants, we can determine the value of Kb. When working problems involving Ka or Kb, if we start with only reactants, we will always make some products. Problems involving acid-base equilibria are just like the equilibria we encountered earlier. We know that acids will ionize in water, so we can write the equilibrium without being given the equation. The values in the Ka expression are in molar and are the values found at equilibrium. The magnitude of Ka or Kb indicates the relative abundance of products versus reactant. In this example, a solution of 0.1 molar of a salt sodium formate is given to determine its pH. Because formic acid is a weak acid, a solution of its conjugate base formate should be basic. First, we write the reaction for the anion with water. We don't have the Kb value, so we must construct an ice table for the reaction. We are assuming that there is no hydroxide at the beginning. Now we have to represent the changes in the concentration in terms of X. As usual, we sum the columns to find the equilibrium concentrations, and we use the relationship this time of Kw, Ka, and Kb. Ka for this substance is 1.8 10 to the negative 4. We substitute into the equilibrium constant expression to find the Kb as 5.6 10 to the negative 11. Because the value of 10 for Kb is very small, we can assume that the change in the concentration of the conjugate base of formic acid formate is small and we can ignore it. Now we solve for X to find the values of the changes. X is 2.4 times 10 to the negative 6. It is always a good idea to check that the approximations used are correct. Now we need to check for the 5% rule. That is, the concentration of any of the species formed at equilibrium divided by the initial concentration of the conjugate base. Or that is 2.4 times 10 to the negative 6 divided by 1 times 10 to the negative 1. The answer tells us that the approximation was valid. Now we have found X, which is equal to the concentration of hydroxide, and we can get the pOH. Or we can use the ion pair of autoionization of water, Kw, to solve for the concentration of hydronium. We will do it both ways. Let's calculate the pH using the self-ionization of water, Kw. We solve for the concentration of hydronium by dividing Kw, 1 times 10 to the negative 14, by the concentration of hydroxide, 2.4 times 10 to the negative 6. The answer is 4.2 times 10 to negative 9, and its negative log gives a pH equal to 8.38, a basic solution as predicted. An alternate method to calculate the pH is to use the concentration of hydroxide calculated from the ice table. Now we have that pOH is minus the log of 2.4 times 10 to the negative 6. The value is 5.62. And then we calculate the pH as 14 minus pOH. In this case, it is 14 minus 5.62. The value is 8.38. Same answer as we got before. It's always a good idea to check that the approximations done are correct. In this case, to check that it's right, we can look at the equilibrium expression and use the values found to determine the Kb value. The answer that we get here is not exactly the same, but it's a good approximation. The actual value is 5.610 to the negative 11, and we got 5.810 to the negative 11.